Tonight, we're going to travel to the very end of everything. Not the end of a civilization, not the end of a planet, not even the end of a galaxy. Tonight, I want to take you somewhere far beyond all of that, to a place in time so distant, so utterly removed from everything you have ever known, that the words we use to describe it will barely hold the weight of what they mean. We're going to travel to the moment when the last star in the universe finally burns out, when the final light, anywhere, in any direction, across the full width of everything that exists, quietly fades and disappears. And what remains after that is something so strange, so silent and so absolute, that it will change the way you look at the night sky tonight. By the end of this journey, you are going to understand exactly why that moment is not just the end of stars. It is the end of almost everything the universe has ever been capable of being. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It is a simple action, but it helps this channel reach more curious minds like yours. Right now, as you settle in and the world around you grows quiet, there are approximately 2 trillion galaxies scattered across the observable universe. Each one holds hundreds of billions of stars. Some of those stars are being born at this very moment, vast clouds of hydrogen collapsing under their own gravity, heating up, igniting, blazing to life in colours of white and blue and gold. The universe, from where we sit tonight, feels almost overwhelmingly alive. It feels permanent. It feels as though it has always been burning and always will be. But here is the thing most people never stop to consider. The universe already passed its peak. Star formation reached its highest point roughly 10 billion years ago. Since then, quietly, without announcement, the rate of new stars being born has been falling. The cosmos is not growing brighter. It is dimming, slowly, relentlessly, and there is nothing, no force, no technology, no act of will anywhere in the universe that can stop it. What you're about to hear is the true story of the universe's long, slow farewell. It is a story measured not in years or centuries or even millions of years, but in timescales so vast that the entire current age of the universe, 13.8 billion years of galaxies and supernovas and civilizations, would appear as a single breath at the very beginning of the tale. We will follow the last stars as they burn down one by one. We will stand in the dark silence after the final light goes out. We will drift through epochs so remote and so cold that the very concept of warmth becomes a memory. And somewhere inside all of that darkness, we will find something unexpected. Something that, in a quiet and terrifying way, makes the light around you right now feel like the most precious thing in the universe. Now, let's begin. There is a question that most people never let themselves ask all the way to the end. Not because it is too difficult or too technical or too far outside the reach of ordinary curiosity, but because somewhere in the middle of asking it, something quietly unsettling begins to settle into the chest, a kind of vertigo, a feeling that the ground beneath everything familiar is not quite as solid as it seemed. The question is this: what happens when the last star in the universe finally dies? Not what happens to one star, not what happens to our sun, or to the galaxy, or even to all the stars alive right now. What happens when the very last one, the final burning point of light anywhere in the entire universe, runs out of fuel, cools down, and goes dark forever? Tonight, that is exactly where we're going. I want you to take a moment before we go any further and just notice where you are right now. Maybe you are lying in bed, the room dim and quiet around you. Maybe there is a window nearby, and beyond it the night sky is doing what it has done every single night of your life, holding its slow, silent parade of stars. Those lights feel ancient and permanent. They feel like they belong to the fabric of things, like they will be there long after you and I are gone, long after everything we know has changed beyond recognition. And in one sense, they are ancient. The light reaching your eyes from some of those stars left its source thousands of years ago. Some of it left before your civilization existed, before your language existed, before your species had even finished becoming what it is today. That light has been travelling through the dark for longer than human history, and it is only now, tonight, arriving at your eyes. But here is the thing most people do not realise. That light is not a promise. It is a receipt. It is evidence of something that happened long ago, something that cannot last forever, something that the universe has already decided will end. Every star you have ever seen, every star that has ever been named or mapped or written about in every culture across the full span of human civilization, every single one of them is burning through a finite supply of fuel. They are not eternal, they are not permanent, they are fires, and fires, no matter how large, no matter how ancient, eventually go out. The universe is not in a steady state, it is in a process. And that process has a direction, and that direction leads, over timescales almost impossible to hold in the mind, toward a darkness so complete that our current night sky would look, by comparison, like the brightest noon of summer. Now, I'm not telling you this to frighten you. That is not what tonight is about. What I want to give you, over the course of this journey, is something rarer and more valuable than fear. I want to give you a true sense of scale, a genuine feeling for the depth of time that stretches out ahead of the universe and what that time actually contains. Because the story of what happens after the last star dies is not simply a story of darkness and cold. It is one of the strangest, most astonishing stories in all of science. It involves epochs so vast that every moment of history you have ever learned about, every empire, every discovery, every war, every love story, would fit into a fraction so small it would be invisible on any timeline we could draw. And yet, within those incomprehensible stretches of time, the universe does not simply sit still. It continues, it changes, it follows rules, patient and indifferent and precise, all the way to a conclusion that no one has ever seen and no one ever will. The era we live in right now has a name. Astronomers call it the Stelliferous Era. It is the age of stars. It began shortly after the Big Bang, when the first hydrogen clouds collapsed under gravity and ignited into the first blazing suns, and it will last for roughly 100 trillion years from that starting point. 100 trillion years? That number is so large it barely feels like language anymore. Our universe is currently 13.8 billion years old. 100 trillion is more than 7,000 times that, and we are right now living somewhere in the early chapters of the Stelliferous Era, close to the beginning, not the middle, not the end. The universe is still relatively young. The stars are still, for the most part, burning strong, but the trend lines are already pointing in one direction and have been for billions of years, and they will not reverse. What comes after the Stelliferous Era is where tonight's journey truly takes us. What comes after is a sequence of epochs, each one longer and darker and colder than the last, that stretch from the death of the final star all the way to timescales that make the current age of the universe look like the first second of a dream. We will pass through the age of cooling stellar remnants, through the age of black holes ruling over an almost perfectly silent cosmos, and finally into something called the Dark Era, a time so remote and so empty that the universe will have become almost indistinguishable from nothing. And through all of it, I will be here with you, moving slowly, not rushing, letting the scale settle into you gradually the way cold settles into a room when the heat has been off for a long time. I think the reason most people never follow this question all the way through is not really fear. I think it is something closer to a failure of imagination. The numbers involved are simply too large for ordinary intuition to process. When someone tells you 1 trillion years, your mind produces a vague sense of a very long time and then moves on. But tonight, we're going to do something different. We're going to use stories and images and comparisons that bring these timescales down to something you can almost feel. We're going to make the end of the universe something you can hold gently in your mind as you drift towards sleep. And somewhere in that process, I think you will find something unexpected. Not despair, not dread, but a kind of profound and quiet wonder. Because the fact that we are here, right now, in the brightest and most eventful era the universe will ever know, is not something to mourn. It is something almost miraculous to notice. So tonight, we go to the end. We go past the last sunrise on any world, past the last warmth reaching any shore, past the final dim glow of the smallest, coldest, most patient star in the cosmos as it too runs out of everything it had and gives into the dark. We follow the universe all the way through, because the universe deserves to be followed, and because you, lying here in the quiet of this night, are one of the vanishingly rare things in all of space and time that is capable of doing the following. You're conscious, you're curious, and you are here, right now, in the only era when any of this light exists to be wondered at. That is worth something. That is worth everything, actually. And by the time this journey is over, I think you will feel exactly why. I want to tell you something that most people never hear. Even though the evidence has been sitting in our telescopes for decades, the universe is not growing brighter. It is not expanding into greater richness, greater complexity, greater light. It passed that peak a long time ago, roughly 10 billion years ago, when the rate of star formation across all of the cosmos reached its highest point, and then, quietly, without drama or announcement, began to fall. We were not there to notice it. There was no one anywhere to notice it. But the decline began nonetheless, slow and steady and absolutely certain, the way a tide turns even when the water still looks high. The universe, right now, tonight, as you lie here listening, is already in the early stages of a process that ends in total darkness. It is already dying. It has been dying for longer than the Earth has existed. Now, I know how that sounds. You look up at the night sky and you see light everywhere. You think about the sun rising tomorrow morning, flooding the world with warmth and colour, and the idea that any of this is in decline feels almost absurd. But the key to understanding what is really happening is to shift your frame of reference. You and I live on timescales of decades. We think of a century as a long time and 1,000 years as nearly incomprehensible history. But the universe operates on timescales billions of times larger than that, and when you zoom out to those scales, the picture changes completely. Imagine you are watching a bonfire from very far away, and from that distance you can see that the pile of wood is finite, that the flames are already lower than they were an hour ago, and that the direction of things is unmistakably toward ash and cold. That is where the universe is right now. The fire is still blazing, but the pile has been shrinking for 10 billion years. The scientific name for the peak of cosmic star formation is sometimes called the cosmic noon. It sounds almost cheerful, like the brightest and most productive hour of the universal day. And in a sense, that is exactly what it was. Around 10 billion years ago, roughly 3 to 4 billion years after the Big Bang first ignited everything into existence, galaxies across the universe were producing new stars at a rate perhaps 30 times higher than they are producing them today. 30 times. Think carefully about what that means. The universe you see tonight, with its 2 trillion galaxies and its hundreds of billions of stars per galaxy, already represents a dramatically quieter, more subdued version of what once was. The cosmic noon blazed, and then the long afternoon came, slow and cooling. And we are living somewhere deep in that afternoon, further from noon than we are from midnight, even if the light around us still feels warm. What drives this decline is not mysterious once you understand the basic logic of how stars are made. Stars are built from gas, primarily hydrogen, the simplest and most abundant element in the universe, produced in staggering quantities in the first few minutes after the Big Bang. Gravity pulls that gas together into vast clouds. The clouds collapse under their own weight, and the pressure and heat at the centre eventually ignite nuclear fusion, and a new star blazes to life. That process has been happening for almost as long as the universe has existed. But every time a star forms, it locks up some of that hydrogen. And every time a star dies, whether it fades quietly into a cooling ember or tears itself apart in a supernova, some of that hydrogen is converted into heavier elements and scattered in forms that are much harder to recycle. The raw material is being used up, slowly but without exception, and there is no new supply arriving from anywhere. The universe is spending down its reserves, and it has been doing so since the very beginning. Galaxies themselves tell this story clearly if you know how to read them. Young, actively star-forming galaxies glow with brilliant blue and white light, the unmistakable signature of hot, massive, newly born stars burning fast and furiously. Older galaxies that have used up most of their available gas shift toward redder, warmer tones, the quieter, mellower glow of older, smaller, slower burning stars winding down their long lives. When astronomers look out across vast cosmic distances and measure the colours of galaxies at different points in the universe's history, they are also looking back in time because light takes time to travel across those distances, and what they see is a universe that was once dominated by that blazing blue-white glow of furious starbirth, gradually, undeniably shifting toward the amber and red of an aging population. It is one of the most profound things observational astronomy has ever shown us. The universe has a colour, and that colour is slowly changing, and the direction of the change is toward darkness. There is something I find quietly extraordinary about this, and I hope you will sit with it for a moment. The fact that we exist at all, that the Earth formed, that life emerged from chemistry, that consciousness arose and began asking questions about the night sky, all of that happened during the long downslope after the cosmic noon. We are not children of the universe's peak. We arrived after it. The most intense, most blazing, most creatively explosive era of cosmic star formation was already billions of years in the past by the time the first living cell divided in some warm, shallow ocean on this young planet. And yet here we are, surrounded by enough starlight to sustain everything we are, alive in an era that still feels, from inside it, like abundance. There is something both humbling and oddly beautiful about that. We caught the long tail of something magnificent, and we are fortunate to be here for even this much of the fire. But the decline does not pause for gratitude, and it does not slow for wonder. The rate of star formation continues to fall, era by era, in every corner of the observable universe. New stars are still being born. Right now, somewhere in the Milky Way, a dense cloud of gas is slowly collapsing toward the pressure point where fusion will ignite and a new sun will blaze to life. But fewer and fewer are being born with each passing cosmic age, and more of the universe's stellar population consists of older stars moving steadily and irreversibly toward their endings. The balance is shifting. The light, almost imperceptibly from where we stand, is thinning. And when you follow that thinning forward honestly, past billions and then trillions of years, past the slow exhaustion of every stellar nursery in every galaxy, you arrive eventually at a universe where star formation has ceased entirely. Not because something catastrophic happened, not because of any accident or collision or failure, simply because the process ran its natural course, the way a river runs to the sea and has no more mountain left to descend. This is the foundation for everything we're going to explore together tonight. The death of the last star is not a sudden event or a cosmic surprise. It is the final note of a song that began almost at the very start of everything, a long, slow, inevitable diminuendo that has been playing since before the Earth existed. The universe has been building toward its own darkness since the moment it first lit up, carrying the end inside the beginning the way every fire carries its own ash. And that, if you let yourself feel the full weight of it quietly here in the dark, is one of the most terrifying and strangely beautiful truths I know. Every star that burns is burning toward its ending. The light exists because it is being spent, and the universe has been saying a very long, very slow goodbye to its own brightness for longer than our world has been alive. Before we can truly understand what it means for the last star to die, we need to understand what a star actually is. Not in the way a textbook defines it, with clinical precision and detached terminology, but in the way you feel it when you stand outside on a clear morning and the sun rises and the warmth hits your face. A star is a fire, a controlled, sustained, almost impossibly powerful fire, held together by two forces locked in a permanent struggle: gravity pulling inward and the energy of nuclear fusion pushing outward. That balance, that tension between collapse and explosion, is what makes a star shine. And the moment that balance tips, in either direction, the star's life is over. Everything a star is, everything it does, everything it gives to the space around it, depends entirely on maintaining that exact, precise, extraordinary equilibrium for as long as its fuel holds out. The story of a star begins long before the star itself exists. It begins in a nebula, a vast, slow-drifting cloud of gas and dust floating through the darkness between other stars. These clouds are mostly hydrogen, with traces of helium and tiny amounts of heavier elements scattered in from the deaths of earlier stars. They are cold, thin, and almost unimaginably large. Some of them stretch across hundreds of light years, which means that if you could travel at the speed of light, covering nearly 6 trillion miles every single year, it would still take you centuries just to cross from one side to the other. These clouds drift and thin and compress over millions of years, disturbed by the shockwaves of nearby supernovas or the gravitational tides of passing objects. And sometimes, In a region where the gas is dense enough and the conditions are just right, gravity wins a local victory. A small pocket of the cloud begins to collapse inward on itself, slowly at first, then faster, pulling more gas toward the centre, growing denser and hotter with every passing 1,000 years. What happens next is one of the most dramatic and beautiful processes in all of nature, even though it unfolds over timescales that make a human lifetime look like a single heartbeat. As the gas cloud collapses, it heats up. This is simply what happens when you compress gas, the same principle that makes a bicycle pump warm when you use it, scaled up to cosmic proportions. The collapsing core grows hotter and hotter, glowing first a dull red, then orange, then brilliant white, as the pressure and temperature climb toward values that are genuinely difficult to hold in the imagination. At the centre of this collapsing cloud, temperatures eventually reach 10 million degrees, and at 10 million degrees, something extraordinary happens. Hydrogen atoms stripped of their electrons are moving so fast and colliding so violently that they begin to fuse together. 4 hydrogen nuclei slam into each other and merge into a single helium nucleus, releasing an enormous burst of energy in the process. Nuclear fusion has ignited, a star has been born. That moment of ignition is the beginning of everything the star will ever be. The energy released by fusion radiates outward from the core in the form of light and heat, and that outward pressure pushes back against the inward crush of gravity. The collapse stops, the star stabilizes. It settles into what astronomers call the main sequence, a long, relatively stable period of its life during which it will burn hydrogen in its core, shine steadily into the surrounding darkness, and do what stars do best, which is illuminate everything around them. For a star like our Sun, this stable period lasts approximately 10 billion years. 10 billion years of steady, reliable burning. 10 billion years of light travelling outward in every direction at the speed of light, warming any planets close enough to receive it, reaching across the darkness toward anything with eyes to see it. It is by any measure an astonishing run. But it is not forever. It was never going to be forever. Here is the thing most people do not fully appreciate when they think about stars. A star does not burn the way a candle burns, consuming its fuel from the outside in, getting smaller and smaller until it is gone. A star burns from the inside out, fusing hydrogen in its core while the vast outer layers sit above, held up by the energy produced below. The core is the engine, and the engine runs on hydrogen. As long as there is hydrogen in the core to fuse, the star shines. But hydrogen is not infinite, and fusion is relentless. Every second, our Sun converts approximately 600 million tons of hydrogen into helium through nuclear fusion. 600 million tons. Every second. That number is so large it almost loses meaning, but what it means in practical terms is that the Sun is gradually, continuously changing its own internal composition. Helium, the ash of hydrogen fusion, accumulates in the core. The hydrogen supply, though enormous, is finite, and a star with a finite fuel supply has, from the moment of its birth, a death already written into its future. The lifespan of a star is determined almost entirely by 2 things: how much hydrogen it starts with, and how fast it burns through it. And here is the counterintuitive part. Bigger stars do not live longer, they live shorter, much shorter. A star 10 times more massive than our Sun burns through its fuel so aggressively, under such extreme gravitational pressure, that it exhausts itself in just a few tens of millions of years. That sounds like a long time until you remember that our Sun has already been burning for 4.5 billion years and has roughly the same amount of time remaining. The massive stars are profligate, burning brilliantly and briefly, blazing with a blue-white intensity that makes our Sun look dim by comparison, and then dying in violent supernova explosions that briefly outshine entire galaxies. They are spectacular, they are wasteful, and they are gone in what amounts to a cosmic eye blink. Smaller stars are the opposite. A star with half the mass of our Sun burns so slowly, so carefully, so efficiently, that it can sustain itself for tens of billions of years, longer than the current age of the universe. And the smallest stars of all, the dim red dwarfs that make up the majority of all stars in the cosmos, burn so slowly and so frugally that they will still be shining long after every star like our Sun has cooled into a dead cinder. They are not dramatic. They are not even particularly bright. You cannot see them with the naked eye from Earth, even the nearest ones. But they will outlast everything else, burning patiently in the dark for trillions of years, the last embers of the stellar era. Understanding this range, from the reckless brilliance of the giants to the patient endurance of the dwarfs, is essential for understanding how the last star will actually look and how and when it will finally go dark. But what I want you to carry with you from this chapter, before we go any further, is something simpler and more fundamental than stellar physics. Every star that has ever existed, every star shining in the sky above you right now, every star that will ever be born in whatever gas clouds still remain in the far future of this universe, every single one of them is a temporary arrangement. They are gravity and gas and nuclear fire held together in a balance that cannot last. They are, in the most profound sense, mortal. They live, they burn, they give everything they have to the space around them, and then they end. And in that sense, as you lie here in the dark and the light of distant suns reaches your window without you even asking for it, there is something in a star's nature that feels, quietly, like something you already know. If you were to line up every type of star in the universe from shortest lived to longest lived, the range you would see would be so extreme that it almost breaks the concept of comparison entirely. At one end, you have stars so massive and so furiously bright that they burn through their entire fuel supply in just a few million years, a duration so brief on the cosmic scale that if the history of the universe were compressed into a single calendar year, these stars would live for less than 3 hours. At the other end, you have stars so small and so miserly with their fuel that they will still be burning long after the universe is 100 times its current age, quietly glowing in near total darkness, the last points of light in an otherwise dead cosmos. Between those two extremes lies the full staggering spectrum of stellar life, and understanding that spectrum is the key to understanding who the last star will be and what it will be like to be alive, if anything is, when it finally goes out. Let us start at the dramatic end, because it is the end most of us instinctively find beautiful. The most massive stars in the universe, the ones astronomers classify as O-type stars, burning with fierce blue-white intensity, are the universe's great spendthrifts. A star with 20 or 30 times the mass of our Sun is so enormously heavy that the gravitational pressure at its core is crushing beyond description, forcing fusion to proceed at a rate that makes our own Sun's consumption look leisurely by comparison. These giants blaze with a luminosity hundreds of thousands of times greater than the Sun, pouring out so much energy that if you could somehow stand on a planet orbiting one of them at the same distance we orbit our own star, the radiation would strip the atmosphere and sterilize the surface in moments. They are magnificent and lethal and short-lived. A star of 30 solar masses will exhaust its hydrogen supply in as little as 3 to 5 million years, swell briefly, and then collapse and explode in a supernova, a detonation so powerful that for a few weeks it can outshine the combined light of every other star in its galaxy. These are the stars that seed the universe with heavy elements. When a massive star explodes, it scatters into surrounding space everything it has spent its short life creating in its core: carbon, oxygen, nitrogen, iron, gold, and dozens of other elements that did not exist in the early universe. Every piece of iron in your blood, every atom of calcium in your bones, every trace of gold ever pulled from the Earth, all of it was forged in the core of a massive star that exploded before our solar system existed. The violence of their deaths is, in the deepest sense, the source of everything complex that has ever existed, including you. But these stars, for all their magnificence, are already gone. Every one of the massive blue giants that blazed through the early universe has long since exploded. The ones you see today are a younger generation, and they too are burning down fast. In the long arc of cosmic time, they are the first to leave the story. Then there are the mid-range stars, the ones like our Sun, classified as G-type yellow dwarfs, though the Sun appears more white than yellow when seen from space. These are the comfortable middle class of the stellar world, not extreme in any direction, not so massive that they burn out in millions of years, not so small that they barely shine at all. A star like our Sun settles into its main sequence life and burns steadily for roughly 10 billion years, which is long enough for planets to form, for continents to rise and erode and rise again, for life to emerge from chemistry and evolve into something capable of looking up and wondering about the source of the warmth on its face. Our Sun is currently about 4.5 billion years old, which means it is almost exactly halfway through its main sequence life. It has roughly 5 billion years left before the hydrogen in its core runs low and things begin to change. 5 billion years of mornings, 5 billion more years of light crossing 93 million miles to warm this small, improbable world. Beyond the Sun-like stars are the orange and red K-type and M-type stars, the smaller, cooler, dimmer members of the stellar family. K-type stars, sometimes called orange dwarfs, burn a little more slowly than the Sun and live significantly longer, some of them for 15 to 30 billion years. They are in many ways among the most hospitable stars in the universe for life, burning steadily and gently for timescales long enough for biology to have enormous amounts of time to develop. Many astronomers suspect that if life is common in the universe, it may be most common around these quiet, patient orange suns. They do not have the drama of the giants or the extreme longevity of the red dwarfs, but they represent a kind of stellar sweet spot, bright enough to warm a planet meaningfully, long-lived enough to give that warmth time to matter, and then, at the far end of the spectrum, there are the red dwarfs. These are the stars that will define the last chapters of the stelliferous era. Red dwarfs, M-type stars, are small, dim, and extraordinarily long-lived. A red dwarf with about 10% of the Sun's mass burns so slowly and so efficiently that it can sustain fusion for 1 trillion years or more. 1 trillion years. To put that in perspective, the current age of the universe is 13.8 billion years. 1 trillion is roughly 72 times that. A red dwarf born today right now, in some newly collapsing gas cloud somewhere in the Milky Way, will still be burning when the universe is 72 times older than it is tonight. It will still be burning when every star like our Sun has long since cooled and gone dark. It will still be burning in an era so remote that there may be nothing else shining anywhere in the observable universe except its faint, dim, reddish glow. Red dwarfs are also, critically, the most common type of star in the universe. Approximately 70 to 75% of all stars in the Milky Way are red dwarfs. They are everywhere, and they are nearly invisible to the naked eye. Not a single red dwarf is close enough or bright enough to be seen without a telescope, even though several of the nearest stars to our own Sun are red dwarfs. Proxima Centauri, the closest star to Earth at about 4.2 light-years away, is a red dwarf with roughly 12% of the Sun's mass. It burns so slowly it will outlive our Sun by an almost incomprehensible margin, still fusing hydrogen long after the Sun has swelled into a red giant and shed its outer layers into space. These humble, invisible, patient little stars will be the universe's last light. They are not what most people picture when they think of stars, but they are the ones who will be there at the end, and when the last one finally goes out, it will likely be alone in a darkness so total and so ancient that the era of our Sun will seem like a distant, half-remembered dream. What strikes me most, thinking about this full range of stellar lives, is how different each type of star's relationship with time actually is. The massive blue giant blazes and dies before a planet like Earth could even fully form. The red dwarf burns so slowly that it will see timescales we have no words for. And somewhere in the middle, our Sun, your Sun, burns steadily through its 10 billion year life, and on one small planet orbiting at just the right distance, that steady light was enough for everything, enough for oceans and mountains and forests and every thought that has ever been thought. One medium star, one medium lifespan, one extraordinary outcome. The last star will be nothing like the Sun. But without stars like the Sun burning in the middle of all that variety, there would be no one to notice when the last one finally goes dark. There are places in this universe so beautiful and so alive that if you could somehow stand at their edge and look inward, you would not have words for what you were seeing. We call them stellar nurseries, vast luminous clouds of gas and dust, where gravity and chemistry and time conspire to do the most extraordinary thing the universe knows how to do, which is turn cold, dark, drifting emptiness into blazing light. The most famous of them, the Orion Nebula, sits about 1,300 light-years from where you're lying right now, and it is actively forming new stars as you listen to these words. If you have ever seen a photograph of it, those billowing curtains of pink and gold and violet gas, lit from within by the fierce young stars just being born at its heart, then you have seen what the universe looks like at its most generative, its most creative, its most alive. These places feel eternal. They feel like the universe's workshops, always running, always producing, always full of the raw noise and energy of creation. But they are not eternal. They are running out of material, and one by one, across the universe, the nurseries are going dark. To understand why the stellar nurseries are disappearing, you have to think about gas the way an economist thinks about a non-renewable resource. The gas that fills these clouds, mostly hydrogen, the primordial material left over from the Big Bang, is the universe's only true currency for making stars. You cannot manufacture more of it from scratch, not in the quantities needed to sustain star formation across cosmic time. Every star that forms locks some of that gas away in its interior, where it will be fused into helium and heavier elements over the star's lifetime. When the star eventually dies, some of that material is returned to space. Supernovas and stellar winds eject enormous quantities of gas back into the interstellar medium, but the returned material is chemically different from what went in. It is enriched with heavier elements, contaminated with the ash of nuclear burning, and much harder to cool and compress into the tight, cold cores needed to birth a new star. Each generation of stars returns the gas a little more polluted, a little less usable, a little less capable of collapsing into something new. In the early universe, this was not a problem because there was so much pristine hydrogen everywhere that the losses barely registered. The cosmic noon, that peak of star formation 10 billion years ago, was possible because the universe was still awash in vast reserves of cold, clean hydrogen gas waiting to be gathered up and ignited. Galaxies were colliding and merging, stirring up their gas supplies and triggering enormous bursts of star formation that lit up the cosmos like a cityscape seen from above on a clear night. The Milky Way itself was much more active then, forming new stars at rates perhaps 10 or 20 times higher than it manages today. But the reserves were being drawn down with every passing billion years, and the rate of replenishment through recycled stellar gas was never quite enough to replace what was being spent. The nurseries grew quieter. The bursts of new star formation became less frequent and less intense. The gas clouds thinned and dispersed, and the spaces between them grew wider and colder and more silent. Today, our own galaxy forms new stars at a rate of roughly 1 to 3 solar masses worth of new stellar material per year, a trickle compared to the roaring flood of cosmic noon. Some of that star formation is still concentrated in recognizable nurseries like the Orion Nebula and the Carina Nebula, regions where gas is still dense enough and cold enough to collapse. But these regions are isolated. They are the last productive patches of a landscape that was once broadly fertile and is now mostly exhausted. Think of them the way you might think of the last cultivated fields at the edge of an advancing desert. Still producing, still alive, but increasingly surrounded by emptiness and not being replenished fast enough to sustain what they once were. The desert is growing, the fields are shrinking, and the direction of things is clear. Look further out across the universe, and the picture becomes even more sobering. Galaxies that were once blazing with star formation have already settled into a quiet old age. Elliptical galaxies, large, rounded, smooth-looking galaxies that contain mostly old stars, have essentially stopped forming new stars altogether. They used up their cold gas supply billions of years ago, often during violent merger events that triggered enormous bursts of star formation and then left the galaxy gas poor and quiet. When you look at an elliptical galaxy today, you're looking at a population of stars that is aging together with no new members joining. The youngest stars in many of these galaxies are already billions of years old. There are no nurseries there. There have not been for a very long time. They are not dying galaxies in any dramatic sense. Their stars are still burning, still shining, but they are coasting on what they have, and what they have is not being renewed. Spiral galaxies like the Milky Way still have some gas left, still have some nurseries still running, still occasionally produce a brilliant new star or cluster of stars that briefly lights up a region of the disk. But the trend lines are unmistakable. The gas supply in the Milky Way is declining. Simulations of galactic evolution suggest that star formation in our galaxy will drop significantly over the next few billion years, and that within perhaps 5 to 7 billion years, roughly coinciding with the death of our own sun, the Milky Way will have used up most of its remaining star-forming gas, and will begin its own long, quiet transition into a galaxy of aging and dying stars with few new ones to replace them. The nurseries will close, not all at once, not dramatically, but one by one, as each remaining cloud of cold gas either collapses into its last generation of stars or disperses too thin to ever collapse again. There is a particular kind of silence that comes to a place after the last young thing has left it. You may have felt something like it in a school building after the final class of the day, or in a park after the last children have gone home, and the swings are still, and the light is going golden and low. It is not an unpleasant silence exactly. It has its own kind of peace, but it carries the unmistakable weight of an ending, the awareness that whatever was alive and noisy and generative here has moved on and will not be coming back. That is the silence that is slowly descending on galaxy after galaxy across the universe. Not all at once, not yet. But the direction is set, the nurseries are dimming, the raw material is running low, and the universe, patient and indifferent and exact, is following its own logic all the way to the place where the last cloud collapses, the last ignition happens, the last new star blazes to life. And then, for the first and final time, no new star follows it. That last star being born is not a moment anyone will mark or celebrate. It will happen quietly, in some corner of some aging galaxy, probably around a red dwarf that will burn for trillions of years in near total isolation. And after it ignites, the universe will never again make anything new from scratch. The nurseries will be empty, the gas will be gone, locked up in stellar remnants and dispersed into forms too thin and too warm to collapse. And the universe will enter a phase it has never been in before, a phase where every source of light is a countdown, where every star still burning is burning toward an ending with nothing coming behind it. The last nursery going dark is not the end of the story, but it is the moment the story stops making new characters. Everything that follows is just the long, slow exit of the ones already on the stage. Of all the stars in the universe, there is one whose death matters to us in a way that no other star's death can. Not because it is the largest, or the most luminous, or the most dramatic in its ending. It is none of those things, but because it is ours. The sun has been rising over this world for 4.5 billion years. It has watched the first oceans form and the first continents rise from shallow seas. It has warmed every living thing that has ever existed on this planet, from the first single-celled organisms drifting in primordial water to every human being who has ever lifted their face toward the sky. It is so constant, so reliable, so deeply woven into the fabric of what life on Earth means that we almost never think of it as something that will end. But it will end. The physics that governs every star in the universe governs our sun too, without exception, without mercy, and without any special consideration for the small blue world circling it at just the right distance. The sun is going to die, and when it does, it will take nearly everything we have ever called home with it. The process will begin, is in fact already beginning, imperceptibly slowly, with the gradual depletion of hydrogen in the sun's core. Right now, the sun fuses roughly 600 million tons of hydrogen into helium every second, and has been doing so for 4.5 billion years. The core has been quietly accumulating helium ash this entire time, and as the hydrogen there slowly runs lower, the core will begin to contract under gravity while the outer layers of the sun begin to expand. This transition will be gradual at first, unfolding over hundreds of millions of years, so slow that no single generation of anything living on Earth would ever notice the change. The sun will grow slightly brighter as it ages. It is already about 30% more luminous than it was when the Earth first formed, and over the next billion years it will brighten enough that the Earth's oceans will begin to evaporate, and the surface conditions will shift beyond what complex life as we know it can sustain. Long before the sun's dramatic final stages, life on Earth will have had to move on, adapt beyond recognition, or end. The sun's slow brightening is, in its own quiet way, already a countdown, but the truly dramatic transformation comes in about 5 billion years, when the hydrogen in the core is finally exhausted. At that point, the sun's core will contract and heat up rapidly, and hydrogen fusion will shift to a shell surrounding the now inert helium core. That shell fusion will release energy at a far greater rate than the core fusion does today, and the outer layers of the sun will respond by expanding outward, slowly at first, then faster, puffing up to sizes that are genuinely terrifying to contemplate from the perspective of any inner planet. The sun will become what astronomers call a red giant. its surface will cool from its current temperature of about 5,500 degrees down to roughly 3,000 degrees, shifting in colour from yellow-white to deep orange-red. But what it loses in surface temperature, it will more than make up for in sheer size. At its peak, the Sun's outer envelope will expand to a radius somewhere between 100 and 200 times its current size, possibly reaching as far as the current orbit of the Earth itself. Let that settle for a moment. The Sun that currently appears as a brilliant disk about half a degree wide in our sky, the Sun that you could cover with your outstretched thumb held at arm's length, will grow until it fills a significant portion of the entire sky. The concept of sunrise will have no meaning anymore, because the Sun will not rise and set in any recognizable way. It will be everywhere above the horizon simultaneously, a vast, dim, red-orange furnace occupying what was once simply called the sky. Mercury will be consumed entirely, swallowed into the Sun's expanding outer layers and vaporized without a trace. Venus will almost certainly follow, and the Earth, our Earth, with its oceans and mountains and every trace of everything that has ever lived here, will either be engulfed directly into the Sun's outer atmosphere, or if it manages to survive at the very edge, will be so thoroughly scorched and stripped by radiation and tidal forces that nothing of its current character will remain. Either way, it will not be a place anymore. It will be debris. After the red giant phase, the Sun will go through additional stages of instability, fusing helium briefly in its core, pulsing and swelling and contracting in cycles, shedding its outer layers in powerful stellar winds that push enormous shells of gas out into the surrounding space. These expelled shells will form what is called a planetary nebula, one of the most visually spectacular objects in all of astronomy, a glowing bubble of ionized gas expanding outward from the dying star, lit from within by the fierce ultraviolet radiation of the exposed stellar core. Some planetary nebulae are almost impossibly beautiful, symmetrical and luminous, and richly coloured in ways that photographs barely do justice to. The Sun's own planetary nebula will expand outward for tens of thousands of years before thinning and dispersing into the interstellar medium, carrying with it the carbon and nitrogen and oxygen that the Sun spent its long life producing. Those atoms will drift in the dark for millions of years and will eventually find their way into new gas clouds, new stellar nurseries, new stars, and perhaps new planets. The Sun's death is not a simple ending. It is also a kind of gift to whatever comes after. What remains after the outer layers have been expelled is the Sun's core, a dense, incredibly hot ball of carbon and oxygen about the size of the Earth, composed of matter so compressed that a single teaspoon of it would weigh several tons. This object is called a white dwarf, and it is not a star in any active sense. It is not fusing anything. It is simply the hot remnant of what the Sun used to be, radiating away its stored heat into space the way a coal from a fire radiates heat after the flame has gone out. It will be blindingly bright at first, shining with the fierce white light of its extreme surface temperature. But it has no fuel source. It is cooling passively, and cooling passively takes an almost incomprehensible amount of time. The white dwarf remnant of our Sun will glow for billions of years, gradually shifting from white to yellow to orange to red as it cools, before eventually fading below the threshold of visibility, becoming what astronomers call a black dwarf, a cold, dark, dead crystal of carbon floating silently in space. This is the fate of our Sun. Not an explosion, not a black hole, not a dramatic final burst of light visible across the galaxy, just a slow, beautiful, terrible unwinding, an expansion into something enormous and red, a shedding of its outer self into glowing shells of gas, and then a long, quiet cooling into darkness over billions of years. There is something in this sequence that I find almost unbearably moving when I sit with it. The Sun has spent 4.5 billion years doing exactly one thing, burning its own substance so that the space around it would not be dark. It has asked for nothing in return. It has not noticed the planet it warmed, or the life that arose on it, or the creatures who looked up at it with wonder and curiosity and gratitude. It has simply burned, faithfully, reliably, completely, until the fuel runs low and the burning changes and the light changes, and finally, over a span of time longer than human civilization could ever witness, the last warmth fades. Every star dies this way, more or less, but this one is ours, and that makes it different in the only way that has ever truly mattered. which is that someone is here, tonight, to know. I want you to imagine a star that you cannot see. Not because it is too far away, though it may be. Not because the night is cloudy, though perhaps it is. But because this star is so faint, so dim, so absurdly modest in the light it puts out, that your naked eye simply cannot register it even when it is one of the closest stars to our own sun. That is the kind of star we're talking about when we talk about the last star. Not a blazing giant, not something magnificent and obvious. The last star will be a red dwarf, one of those small, cool, patient, nearly invisible embers of stellar life that make up the overwhelming majority of all stars in the universe, and yet are so underwhelming in individual appearance that most people have never thought about them at all. The universe's final light will not go out with a bang. It will not even go out with a flicker you could easily see from a distance. It will simply cool and dim and fade in the way that the least dramatic things in the world so often do. Red dwarfs are, in almost every measurable way, the opposite of the brilliant blue giants we encountered earlier in our journey. Where a blue giant might contain 20 or 30 times the mass of the Sun, a red dwarf typically holds somewhere between 8% and 50% of the Sun's mass. Where a blue giant burns at surface temperatures of 30,000 degrees or more, blazing with fierce ultraviolet and blue-white light, a red dwarf burns at surface temperatures of roughly 2,000 to 4,000 degrees, cool enough, as stars go, that its light shifts well into the orange and red end of the spectrum. Where a blue giant shines with a luminosity hundreds of thousands of times greater than the Sun, a red dwarf may shine at less than 1% of the Sun's luminosity, producing so little light that a planet would need to orbit extremely close to it just to receive enough warmth to potentially support liquid water. Everything about a red dwarf is reduced, conservative, economical, and that economy is precisely why they last so long. Here is the thing most people find surprising when they first learn about red dwarfs. Because they are so small and their cores are under so much less gravitational pressure than larger stars, they actually fuse their hydrogen far more efficiently and more completely than stars like the Sun. Our Sun, over the course of its 10 billion year life, will only actually fuse about 10% of its total hydrogen supply. The rest sits in the outer layers, never reaching the core conditions needed for fusion. A red dwarf, by contrast, is fully convective, meaning that the gas in its interior circulates throughout the entire star, continuously bringing fresh hydrogen down into the core to be fused. A red dwarf uses nearly all of its hydrogen, not just the fraction in its core. It is the difference between a car engine that burns its fuel completely and efficiently, and one that wastes most of what it consumes. The red dwarf wastes almost nothing. It burns slowly, completely, and for almost unimaginable length of time. How long? For the smallest red dwarfs, those hovering just above the minimum mass needed to sustain nuclear fusion, around 8% of the Sun's mass, the answer is approximately 1 trillion years. 1 trillion. To help you feel that number rather than just hear it, consider this. The universe is currently about 13.8 billion years old. 1 trillion years is roughly 72 times that. If the universe's current age were compressed into a single day of 24 hours, a small red dwarf born today would still be burning at the end of 72 such days, more than 2 months later on that compressed timeline. And the red dwarfs already in existence, the ones already burning right now in the darkness around our solar system, have barely even started. Proxima Centauri, our nearest stellar neighbour at 4.2 light-years away, is a red dwarf estimated to have a total lifespan of about 4 trillion years. It is, in cosmic terms, a newborn. It has barely touched its fuel supply. It has almost everything still ahead of it. Now try to picture what the universe will look like in the era of the last red dwarf, the current age of the universe, 13.8 billion years of galaxies and supernovas and planets and life and civilizations will be a vanishingly small sliver at the very beginning of the timeline. Our Sun will have been dead for so long that the white dwarf it left behind will have cooled to near invisibility. Every star like the Sun that has ever existed will be gone. The blue giants, the orange dwarfs, the yellow stars. All of them will have long since exhausted their fuel and faded into cold, dark remnants drifting silently through space. The galaxies themselves will have changed beyond recognition. Their spiral arms dissolved, their gas supplies exhausted, their stellar populations thinned to a sparse scattering of cooling embers, and the last few red dwarfs still burning. The Milky Way will not look like the Milky Way. It will look like something much older, much quieter, much emptier, a faded shadow of what it once was, held together by gravity but hollow of everything that once made it vibrant. And in that darkness, scattered impossibly far apart across what remains of the observable universe, the last red dwarfs will still be burning. Not close together, not in clusters or nurseries or star-forming regions, because all of those will be long gone. They will be isolated, solitary. Each one a faint point of dull, reddish light in a sky that contains almost nothing else to see. If there were eyes anywhere capable of looking at that sky, and it is difficult to imagine what kind of being could exist in such a universe, if any, the night sky would be almost completely black. Not the richly populated darkness you see when you look up tonight, with its thousands of visible stars and the faint smear of the Milky Way stretching overhead. A true darkness, vast and nearly total, broken only by the occasional dim red point of a dying dwarf star visible only at close range. The universe will be, by any emotional definition of the word, a lonely place. The last star of all will not announce itself. There will be no signal, no special radiation, no event that marks it as the final one. It will simply be the last red dwarf left burning when all the others have finally cooled and gone dark, one by one, over the course of hundreds of trillions of years. It will be burning the same way it always burned, dim, slow, patient, red, in a universe that has become almost indistinguishable from total emptiness. Its surface will be cool and quiet by stellar standards. The fusion in its core will be sputtering through its last reserves of hydrogen, the reaction slowing as the fuel thins, and then, over a period of time that may itself span millions of years, it will simply cool, the fusion will cease, the light will dim to nothing, the last warmth in the universe will dissipate into the surrounding cold, and the stelliferous era, the age of stars that began with the first ignition after the Big Bang and stretched across 100 trillion years of cosmic history, will be over, complete, finished. And the universe, for the first time since a fraction of a second after its own birth, will contain no light that was not made an almost incomprehensible length of time ago. The dark will be total, and the next chapter of the universe's story will begin in silence. I want to take you somewhere no human being has ever been, and no human being ever will be. Not in body, not in any spacecraft we could ever build, not in any form of physical presence we currently understand. I want to take you there in the only way it is actually possible to go, in the imagination, in the quiet space between wakefulness and sleep, where the mind is loose enough to hold things too large and too strange for ordinary daylight thinking. I want to take you to the moment the last star dies, not the general era, not the approximate epoch, the actual moment, the final cooling, the last light, the precise instant when the universe, for the first time in 100 trillion years, contains no active fusion anywhere within it. No fire, no warmth being generated anywhere, just the long, cold, dark aftermath of everything that came before. That moment is real. It is written into the physics of this universe as surely as anything that has ever happened. And tonight, you and I are going to stand at its edge together. Picture the scene as slowly and carefully as you can. The universe is unimaginably old. Roughly 100 trillion years have passed since the Big Bang, give or take the particular lifespan of whatever red dwarf happens to be the last one burning. The cosmos around this final star is nothing like the universe you know. The expansion of space has continued for all of that time, pushing everything farther and farther apart so that the distances between any remaining objects are staggering even by the standards of the universe we inhabit tonight. The cosmic microwave background radiation, that faint afterglow of the Big Bang that fills all of space even now, has been stretched by the expansion to wavelengths so long they are utterly undetectable by any instrument we could imagine. The temperature of space itself, already close to absolute zero today at just 2.7 degrees above absolute zero, has dropped even further to a fraction of a degree above the coldest temperature that can exist. The universe is not merely cold, it is as close to the cold of true nothingness as physics allows, while still technically being something. The galaxies, or what remains of them, are unrecognizable. The Milky Way merged with Andromeda billions of years ago, and that merged galaxy has itself long since relaxed into a diffuse, roughly elliptical cloud of stellar remnants. White dwarfs that have cooled toward darkness, neutron stars spinning silently in the void, the occasional black hole drifting through the emptiness with nothing nearby to consume. The intricate spiral structure, the star-forming arms, the glowing core, the nebulae and clusters and all the visual richness of a living galaxy, all of that is gone. What remains is a sparse, irregular scattering of dead and dying objects, held together loosely by gravity but carrying almost none of the energy or complexity that once made a galaxy something magnificent to behold. And somewhere in this dim, dispersed, nearly structureless remnant of what was once a great galaxy, the last red dwarf is burning. It is small. It has always been small. Through its entire multi-trillion-year life, it has never been anything other than a dim, reddish, modest little star, the kind of object that barely registers as a star at all when you compare it to the blue giants and yellow dwarfs that blaze through the universe's earlier eras. But it has outlasted all of them by margins so vast they have no good analogy. Every other star in the history of the universe, every single one of the estimated 1 septillion stars that have ever burned across the full span of cosmic time, has already run its course and gone cold. This one is the last. It does not know it is the last. It does not know anything. It is simply a ball of gas held together by gravity, fusing its last reserves of hydrogen in its core, radiating a dim reddish light into a darkness so total that the light barely seems to matter, but it matters. As long as it is burning, the stelliferous era is not over. As long as this one small star is fusing hydrogen, the universe still contains what it has contained since nearly the very beginning, a fire somewhere in the dark. The end does not come suddenly. That is the first thing to understand. A red dwarf does not explode when its hydrogen runs out the way a more massive star might. It does not swell into a red giant and shed its outer layers in a dramatic nebula. It simply cools. As the hydrogen in its fully convective interior approaches exhaustion, the rate of fusion slows. The energy output from the core decreases. The outward pressure that has balanced gravity for trillions of years begins to weaken slightly, and the star contracts a little, growing denser and dimmer. The surface temperature drops. The colour shifts from its already dim red toward a deeper, darker, duller infrared glow that would be invisible to human eyes even at close range. The star becomes effectively a brown dwarf, a failed star, an object that is still technically warmer than the surrounding space, but no longer sustaining active fusion in any meaningful sense. And then that residual warmth too begins to radiate away, degree by degree into the surrounding cold, until the object's temperature approaches the ambient temperature of the universe itself. At that point, for all practical purposes, the light is gone. No radio transmissions mark this moment. No signal travels across the universe to announce it. No record is kept anywhere in any form that could be read. The last light simply goes out the way all lights go out when there is nothing left to sustain them, quietly, gradually, without drama, without witness. The photons that the last star emitted in its final moments will continue travelling outward at the speed of light for as long as the universe exists, carrying their tiny parcels of energy across an increasingly empty and cold cosmos, never arriving anywhere in particular, never being absorbed by anything that could use them, or notice them, or remember them. They are the last messengers of the stelliferous era, travelling forever through a universe that has moved on from the era they represent. If that is not one of the most haunting images in all of science, I do not know what is. And then there is the silence, not the silence you know, the silence of a quiet room, or a night with no wind, or a moment between sounds. This is a different kind of silence entirely. It is the silence of a universe in which no process anywhere is generating new light, no fusion, no stellar wind, no glowing nebula, no accretion disk heating up around a feeding black hole. Those will still exist technically, but they are not stars, and they are not what the universe was built to produce. The silence after the last star is the silence of a universe that has spent its greatest inheritance. Everything that stars made possible, warmth, chemistry, complexity, life, thought, wonder, all of it depended on that continuous supply of stellar energy that is now finally exhausted. The universe will continue to exist for far longer than the stelliferous era lasted. But it will exist in a fundamentally different mode. not as a place where things are made and lit and warmed, as a place where things that were made long ago slowly, patiently, inevitably decay. The last light going out is not the end of the universe, but it is the end of the universe as a place where the darkness is ever broken by something new, and that, in ways I find genuinely difficult to fully hold, is terrifying and beautiful and real. After the last star dies, the universe does not end. That is perhaps the most important and most disorienting thing to understand about where we're going next. The universe continues, it expands, it follows its laws, it persists, in its way, for timescales that make the entire stelliferous era, 100 trillion years of stars and light and warmth, look like a brief, bright opening act. What comes after the last star is an epoch astronomers call the degenerate era, and it is one of the strangest, most alien phases of existence that physics allows. No stars burn in this era, no new light is generated anywhere. The universe is dark in a way that is qualitatively different from the darkness between stars that you might imagine when you close your eyes and think of space. It is not the darkness of a night sky, which is full of stars if you know where to look. It is the darkness of a universe that has genuinely run out of fire. And yet in that darkness, things still exist, objects still drift, structures still hold together loosely under gravity. The universe in the degenerate era is not empty. It is full of ghosts. The ghosts are the remnants of everything stars used to be. When a star like our Sun dies, it leaves behind a white dwarf, a dense, hot core of carbon and oxygen, roughly the size of the Earth, but containing most of the star's original mass, radiating its stored heat slowly into the surrounding cold. In the early degenerate era, the universe still glows faintly from the residual heat of countless white dwarfs left over from the stelliferous era. There are a lot of them. Estimates suggest that the vast majority of all stars that have ever existed will end their lives as white dwarfs, which means the degenerate era begins with an enormous population of these objects scattered across every former galaxy. They are not stars, they are not fusing anything, but they are warm, and for a time, a very long time by human standards, though brief by the standards of what comes next, they radiate a faint, diffuse warmth into the surrounding darkness. The universe in its early degenerate era is not completely cold. It is just very, very dimly lit, and getting dimmer by the age. But white dwarfs cool. That is the fundamental, inescapable truth of their existence. With no internal energy source to replace what they radiate away, they simply lose heat continuously, shifting from white to yellow to orange to red to infrared as their surface temperatures drop over billions and then trillions of years. The timescale for a white dwarf to cool to complete darkness, to become what is called a black dwarf, a cold, inert crystal of carbon and oxygen drifting silently through space, is estimated to be somewhere around 1 quadrillion years or more. 1 quadrillion years is 1,000 trillion years, which is itself about 70 times longer than the stelliferous era. So the cooling of the white dwarfs is not a quick process even by cosmic standards. For a very long time after the last star dies, the universe contains a slowly fading population of cooling stellar remnants, each one a little dimmer and a little colder than it was the era before, the collective warmth of a dead stellar civilization dispersing gradually into the void. It is in a way the longest sunset in history. Alongside the white dwarfs, the degenerate era also contains neutron stars, the remnants of more massive stars that ended their lives in supernova explosions. A neutron star is one of the most extreme objects in the known universe, packing roughly 1 to 2 times the mass of the Sun into a sphere only about 20 kilometers across. The density of a neutron star is so extreme that a single teaspoon of its material would weigh billions of tons on Earth. Neutron stars spin, sometimes hundreds of times per second, and emit beams of radiation that sweep across space like cosmic lighthouses. These are the objects we call pulsars when one of those beams happens to sweep across Earth. In the degenerate era, pulsars gradually slow their rotation as they lose energy to radiation, eventually becoming quiet, cold, dark neutron stars spinning almost imperceptibly in the void. Like the white dwarfs, they cool and dim over unimaginable timescales, becoming yet another species of ghost in a universe increasingly populated by the cold remnants of what once was bright. The largest ghosts of all are the black holes. Scattered throughout what were once galactic centers and dense stellar clusters, black holes survive the death of the stelliferous era completely unchanged, because they were never burning in the first place. A black hole is not a remnant of a fire that went out. It is a region of space where gravity has become so extreme that not even light can escape. It does not cool. It does not radiate heat in any conventional sense. It simply sits, patient and permanent seeming, holding its mass, bending space around it, waiting. In the early degenerate era, black holes occasionally still have things to consume. A white dwarf drifting too close and being torn apart by tidal forces, a neutron star falling in after a long gravitational dance, a wandering cold remnant pulled slowly across the eons into the event horizon. But these events become rarer and rarer as the population of drifting objects thins, as gravitational interactions slowly scatter most objects out of the remnant galaxies into the intergalactic void, leaving the black holes increasingly alone at the centers of increasingly empty structures. They are the kings of the degenerate era, but they reign over almost nothing. What does it feel like, if feel is even a word that makes sense here, to exist in the degenerate era? Imagine drifting through space in complete darkness. No stars visible anywhere. The sky in every direction is black, not the deep blue-black of a clear night on Earth with its rivers of stars, but a true, absolute, unbroken black with only the faintest, most distant smudges of cooling white dwarfs visible if you happen to have instruments sensitive enough to detect their dwindling infrared glow. The temperature of the surrounding space is barely above absolute zero, perhaps a millionth of a degree above the coldest possible temperature, growing colder still as the universe continues to expand and the remnant radiation continues to thin. The silence is not merely the absence of sound, which cannot travel through space in any era. It is the silence of an almost total absence of events. Almost nothing is happening anywhere. Almost nothing is changing. The universe is coasting slowly through its own aftermath, carrying the cold debris of everything it used to be. And yet, even in this era of ghosts and cooling embers, something remarkable and deeply strange is theorized to occur. Physicists who study the ultimate fate of matter have proposed that protons themselves, the fundamental particles that make up the nuclei of every atom in every object in the universe, may not be perfectly stable over sufficiently long timescales. If protons decay, as some theoretical model suggests they might, then even the cold, inert white dwarfs and black dwarfs and neutron stars of the degenerate era will not last forever. They will dissolve, atom by atom, over timescales of perhaps 10 to the 34th power years, a number so large that writing it out would require 34 zeros after the 1. Whether proton decay actually occurs is something we do not yet know with certainty. It has never been observed. But if it does, then not even the ghosts are permanent. Even they will fade. Even the cold crystals of carbon left behind by dead stars will eventually dissolve into their most fundamental constituents and drift away as radiation. Nothing in the degenerate era is truly immortal. Everything, given enough time, becomes something less. The universe of ghosts is itself a temporary arrangement, and what comes after even the ghosts are gone is something stranger still. There is a point in the future of this universe, unimaginably far ahead of where we are right now, far even beyond the death of the last star, when nearly everything that once existed will be gone. The white dwarfs will have cooled to black. The neutron stars will have slowed their ancient spinning and grown cold and dark. The ordinary matter that made up planets and moons and asteroids and all the complex, beautiful, improbable structures of the stelliferous era will have either been consumed, dispersed, or, if proton decay is real, dissolved into radiation over timescales so vast they have no honest analogy in human experience. And when all of that has happened, when the degenerate era has run its extraordinary length and the last cold remnants of stellar civilization have faded below any threshold of detection, one class of object will remain, not burning, not radiating heat in any conventional sense, not doing anything that looks, from the outside, like activity, but present, massive, patient beyond all comprehension. The black holes will still be there, and for a span of time that dwarfs everything that came before it, the universe will be theirs. To understand why black holes outlast everything else, you have to understand what they actually are. Not as frightening abstractions, but as physical objects with specific properties. A black hole forms when a sufficient amount of mass is compressed into a small enough volume that the gravitational field at its surface becomes so intense that the escape velocity exceeds the speed of light. Since nothing in the universe can travel faster than light, nothing that crosses the boundary of a black hole, the event horizon, can ever escape. Not matter, not radiation, not information of any kind, at least not in any form we currently understand. Whatever falls in stays in, adding its mass to the black hole's total, making it slightly more massive, slightly larger, slightly more gravitationally dominant than it was before. Black holes do not burn, and they do not cool, and they do not decay through any of the processes that undo every other object in the universe. They simply accumulate and persist and wait. In the black hole era, the epoch that follows the degenerate era, black holes are the dominant feature of the universe not because they are everywhere, but because everything else has effectively ceased to be a significant presence. The universe at this point is almost perfectly empty by any measure that would have made sense to an observer in our current era. The distances between the remaining black holes are staggering, stretched by billions of additional years of cosmic expansion, to scales that make the current observable universe look compact by comparison. These black holes drift through an almost perfect void, occasionally interacting gravitationally with one another over timescales of quadrillions of years, sometimes merging when two happen to pass close enough to spiral together, each merger creating a slightly larger, slightly more massive remnant. They are unhurried. They have no reason to hurry. The universe around them is going nowhere, doing nothing, offering no urgency of any kind. They are the last kings of a kingdom that has been emptied of almost everything else, presiding over a realm of cold and darkened distance that extends in every direction without limit. What is a black hole actually like as an object? The event horizon is not a physical surface. If you were somehow falling toward one, you would not feel a boundary as you crossed it. You would simply pass a point of no return, a threshold defined entirely by geometry and gravity, beyond which the direction toward the singularity becomes as unavoidable as the direction of time itself. Inside the event horizon, space and time swap their roles in a way that is genuinely impossible to fully picture with normal intuition. The singularity at the center is not a place you are traveling toward so much as a moment you are traveling toward, a future that cannot be avoided. Outside the event horizon, the black hole makes itself known through its gravitational influence, bending the paths of anything that passes nearby, warping space in ways that would distort any light passing close enough to its edge. In the black hole era, with so little matter and so little light anywhere in the universe, even this gravitational warping goes largely unwitnessed. The black holes bend a space that contains almost nothing to bend around. For most of the history of physics, black holes were considered essentially permanent objects. Once formed, the thinking went, they simply existed indefinitely, accumulating whatever fell into them, changing only by growing. But in the 1970s, the physicist Stephen Hawking made a discovery that changed that picture entirely and introduced one of the most haunting and beautiful ideas in all of theoretical physics. Hawking showed, through a careful combination of quantum mechanics and general relativity, that black holes are not perfectly black, they radiate, not because anything is escaping from inside the event horizon that remains impossible, but because of quantum effects at the boundary of the event horizon itself. In the language of quantum mechanics, empty space is not truly empty. It seethes with what physicists call virtual particles, pairs of particles and antiparticles that spontaneously appear and annihilate in fractions of an instant. Near the event horizon of a black hole, occasionally one particle of a pair falls inward while the other escapes outward into space. The escaping particle carries away a tiny amount of energy, and because energy and mass are equivalent, as Einstein showed, this means the black hole loses a tiny, almost infinitesimal amount of mass with each such event. The black hole is evaporating, incredibly slowly, but evaporating nonetheless. The rate of Hawking radiation is inversely related to the mass of the black hole. The more massive the black hole, the slower it evaporates. For the stellar mass black holes that form from collapsing stars, the evaporation timescale is already almost beyond comprehension. A black hole of 10 solar masses would take approximately 2 times 10 to the power of 74 years to evaporate completely through Hawking radiation. That number, a 2 followed by 74 zeros, is so much larger than the current age of the universe that writing it out in full would fill pages. and the supermassive black holes that lurk at the centers of galaxies, containing millions or billions of solar masses, take proportionally longer still. The largest known black holes, the ultramassive ones containing tens of billions of solar masses, may take something on the order of 10 to the power of 100 years to fully evaporate. One followed by 100 zeros. A Google years. The universe will be a place of almost perfect emptiness for almost all of that time, waiting patiently as its last and greatest structures slowly, particle by particle, dissolve. But dissolve they will. That is the crucial point. That is what makes Hawking radiation one of the most profound ideas in physics, and one of the most quietly terrifying things I know about the universe's future. Even the black holes are not forever. Even these massive, patient, indestructible-seeming kings of the late universe are subject to a process of slow, inevitable dissolution. They will reign for timescales that make the entire history of stars look like a single breath. They will persist long after every other structure in the universe has ceased to exist in any recognizable form. But they will end. One by one, over those incomprehensible timescales, each black hole will reach a critical point in its evaporation, where its mass becomes small enough that the radiation accelerates dramatically, and it expires in a brief intense burst of energy. A final flash of gamma rays emitting into a universe that contains almost nothing left to receive them. And when the last black hole evaporates, when that final burst of radiation disperses into the surrounding void, the black hole era will be over, and what remains will be something that the word emptiness barely begins to describe. Let me try to give you a feeling for how long the black hole era actually lasts. Not just the number, because the number alone does nothing. It slides off the mind the way water slides off glass, leaving no impression, no residue, no genuine sense of what it means. What I want to give you is something closer to the experience of that time, even though no experience of it is actually possible for anything we would recognize as a living mind. So let us build toward it slowly, the way you build towards sleep, by letting go, layer by layer, of the familiar. Start with the age of the universe as it is tonight. 13.8 billion years. Hold that. Now multiply it by 1,000. You are now at 13.8 trillion years, a time so far beyond the present that every star currently burning in the sky will long since have died and cooled and gone dark. Now multiply by another 1,000. 13.8 thousand trillion years. The last red dwarf has been cold for an almost incomprehensible length of time. The white dwarfs have cooled toward black. The degenerate era is well underway. Now multiply by another 1,000, and another, and another. Keep multiplying, keep letting each new number render the previous one negligible, and you will begin to approach, only begin to approach, the timescales over which the largest black holes evaporate through Hawking radiation. The black hole era is not a long chapter. It is the chapter that makes all other chapters invisible. The physics of Hawking evaporation is worth understanding in a little more detail, because it is one of those ideas that becomes more astonishing the more carefully you look at it. The process begins at the edge of the event horizon, in what physicists describe as the quantum vacuum, the seething, fluctuating baseline state of space itself. In quantum mechanics, there is no such thing as truly empty space. Even in a perfect vacuum, the uncertainty principle of quantum physics ensures that energy is constantly and spontaneously fluctuating, producing pairs of virtual particles, a particle and its corresponding antiparticle, that appear together, exist for an immeasurably brief moment, and then annihilate each other and vanish. In ordinary space, far from any black hole, this process is perfectly balanced and produces no net effect on anything. But at the edge of a black hole's event horizon, the geometry of space is so extreme that occasionally one particle of a newly formed pair falls across the horizon before the annihilation can occur, while its partner escapes outward into the surrounding space. That escaping particle carries real energy, energy that had to come from somewhere, and that somewhere is the black hole itself. With each such event, the black hole loses an infinitesimal fraction of its mass. The process is real, it is slow beyond all comprehension. But it is relentless, and it has all the time in the universe. For the smallest black holes, those of just a few solar masses left behind by collapsed stars, the evaporation is the fastest, though fast here is a relative term that would make any human sense of patience seem laughably inadequate. A black hole of 10 solar masses will radiate away its mass over a period of roughly 2 times 10 to the 74th power years. To write that number out, you would write a 2 and then place 74 zeros after it. The entire current age of the universe, all 13.8 billion years of it, is a 1 followed by 10 zeros. The evaporation time of a small black hole is a 2 followed by 74 zeros. The current age of the universe does not even register as a rounding error on that timescale. It is less than a single tick of a clock measuring time in units of 10 to the 74th years. And yet, eventually, given enough time, even that small black hole reaches the end of its evaporation. It shrinks. It heats up as it shrinks. Hawking radiation becomes more intense as the mass decreases and the event horizon shrinks, a runaway process that accelerates toward its conclusion. And in a final burst of energy lasting only a tiny fraction of a second, the black hole completes its evaporation and vanishes entirely, leaving behind only a brief flash of radiation dispersing into the surrounding cold. The supermassive black holes at the centers of galaxies take proportionally, almost unimaginably longer. A black hole of 1 billion solar masses, a modest supermassive black hole by galactic standards, evaporates over a period on the order of 10 to the 83rd power years. The largest ultramassive black holes known, containing tens of billions of solar masses, may require something approaching 10 to the 100th power years, what mathematicians call a googol, a number so large that it exceeds the total number of atoms in the observable universe by many orders of magnitude. These objects will still be present, still massive, still bending the space around them, when everything else in the universe has long since dissolved into diffuse radiation. They are the last structures, the last places in the universe where gravity has gathered mass into something coherent and localized. And they will go one by one in ascending order of size, each smaller black hole vanishing in its final burst of Hawking radiation before the larger ones, until only the ultramassive giants remain, sitting alone in an almost perfectly featureless universe, evaporating at a rate so slow it would be meaningless to describe. What is the universe like during this process, in the long waiting time between the beginning and end of black hole evaporation? It is, by any honest description, almost nothing. The expansion of space continues, driven by dark energy, pushing any remaining objects, and there are very few, to distances so vast that the concept of neighbouring structures becomes meaningless. The temperature of the universe drops so low that it approaches a number called the Hawking temperature of the largest remaining black holes, an extraordinarily tiny temperature, a tiny fraction of a degree above absolute zero, representing the faint warmth radiated by the evaporating black holes themselves. This is the only warmth left anywhere in the cosmos. It is not warmth you could feel. It is not warmth that could sustain any chemical process, any reaction, any event more complex than the occasional random collision of 2 stray photons drifting across the void. It is warmth only in the mathematical sense, a temperature slightly above the minimum. The universe in this era is about as close to absolute nothing as a something can be, while still technically being something. And here is the thought I want to leave you with as we stand in the middle of this almost incomprehensible era of slow dissolution. Every black hole that evaporates does so by converting its mass into radiation, into photons, into particles, into the most fundamental forms of energy the universe knows how to make. The mass that fell into that black hole, perhaps the remnants of stars, perhaps the debris of planets, perhaps material that was once part of living creatures on some world that existed billions of years before even our Earth formed. All of that mass is being returned to the universe, transformed, unrecognizable, in the form of radiation drifting outward at the speed of light through an almost empty cosmos. Nothing is truly destroyed. Everything is transformed. The matter that made up the universe does not disappear when the black holes evaporate. It becomes light, the most fundamental and indestructible thing the universe knows how to produce. And that light, those final photons from the last evaporating black holes, will travel through the dark era that follows for as long as the universe itself continues to exist. They are the last echoes of everything that ever was, faint beyond all measurement, travelling forever, going nowhere in particular. But still, in some sense, that feels important, even if I cannot fully articulate why, still there. When the last black hole finishes its final burst of Hawking radiation, and the brief flash of its ending disperses into the surrounding void, the universe enters a state that has no good name in any human language. We call it the Dark Era, but that name feels almost embarrassingly inadequate for what it actually describes. Darkness, as you experience it tonight lying in your room, is the absence of visible light, but it is filled with air, with warmth, with the faint sounds of a world still active just outside your walls. The darkness you know is temporary and local, and surrounded on all sides by the implicit promise of light returning. The Dark Era is nothing like that. It is darkness in an absolute sense, a state in which no light is being generated anywhere in the observable universe, in which no warmth exists above a temperature so close to absolute zero that the difference is physically meaningless, in which space continues to expand, carrying almost nothing with it, except a thin, diffuse, cooling haze of the most fundamental particles physics knows, drifting farther and farther apart with each passing eon, never interacting, never combining, never forming anything. It is the universe at the end of its own story, still existing in the strictest physical sense, but doing almost nothing with that existence. What actually remains in the Dark Era? The inventory is brief and strange. There are photons, particles of light released during the long evaporation of black holes, travelling at the speed of light through a universe that has nothing left for them to interact with, red-shifted by the continued expansion of space to wavelengths so enormous they carry almost no energy at all. There are electrons and positrons, the lightest charged particles, drifting through the void at vast separations, too diffuse and too cold to find each other and annihilate in any reasonable time frame. There are neutrinos, those near-massless ghost particles that barely interact with anything even under normal circumstances, now truly alone in a universe where there is essentially nothing for them to interact with at all. There may be gravitinos or other hypothetical remnant particles depending on the precise details of physics we do not yet fully understand. And there is dark energy, still present, still driving the expansion of space, still doing the one thing it has always done, which is push everything apart, though there is almost nothing left to push. That is the complete contents of the universe in the Dark Era, not a rich inventory, not a place where things happen in any meaningful sense, just the final dispersed cooling residue of 100 trillion years of stellar fire and billions more years of slow black hole evaporation, spreading thinner and colder through an expanding space that will never stop growing. The temperature of the Dark Era universe is something that requires a moment of careful imagination to appreciate, because it is not zero, and the fact that it is not zero is itself significant. Absolute zero, the coldest possible temperature, is the state in which all thermal motion ceases entirely, and no energy of any kind moves from place to place. The Dark Era universe will approach absolute zero asymptotically, meaning it will get closer and closer to it without technically ever reaching it, the way a line on a graph can approach an axis forever without quite touching it. The residual radiation left over from black hole evaporation gives the universe a temperature almost incomprehensibly close to absolute zero, but not exactly zero. As the universe continues to expand, that radiation stretches and cools further, the temperature dropping by fractions of a degree over timescales that dwarf even the black hole era. There is, in the most technical physical sense, still something happening in the Dark Era universe. Energy still exists, particles still move, however slowly, but the gap between what is technically happening and what could meaningfully be called activity is so vast that the distinction feels almost philosophical. Here is the thing about the Dark Era that I find most quietly terrifying when I sit with it long enough. It is not a brief transition. It is not a passage between two more interesting states that last a manageable length of time. The Dark Era, if it goes on indefinitely, and current physics gives us no reason to think it does not, is by far the longest phase of the universe's existence. The Stelliferous Era, with its 100 trillion years of stars and light, is a brief bright flicker at the very beginning of the timeline. The Degenerate Era, stretching across timescales measured in powers of 10 that dwarf ordinary language, is itself brief compared to the Black Hole Era. And the Black Hole Era, those incomprehensible googles of years during which the last structures slowly evaporate, is itself a finite chapter with a definable end. The Dark Era has no defined end. It continues, and continues, and continues. Growing colder, growing emptier, the distances between any remaining particles growing larger with every passing eon, the universe becoming, with each additional stretch of time, more perfectly and absolutely alone with itself. Physicists sometimes describe the Dark Era using the language of thermodynamic equilibrium, the state in which a system has reached maximum entropy, meaning all the energy that could have flowed from one place to another already has, and everything is now at the same temperature, and no further work can be extracted from any process, because there is no temperature difference anywhere to drive it. This state is sometimes called the heat death of the universe, though the name is misleading because heat is precisely what is absent. It is better described as the cold death, the stillness death, the death by perfect sameness. In a universe at thermodynamic equilibrium, nothing can happen because everything that could happen already has. The universe does not disappear. It does not collapse or explode or transform. It simply reaches a state of such profound, such absolute, such permanent uniformity that change becomes physically impossible. It exists, but it does nothing with its existence. It is a universe that has become, in the most complete sense imaginable, inert. And yet, and this is where the story takes an unexpected turn that I want to hold back just a little longer, because it deserves its own space. Quantum mechanics, the same framework that gave us Hawking radiation, and the uncertainty principle and so many of the stranger truths of modern physics, does not allow perfect stillness at the quantum level. Even in a universe at maximum entropy, even in the coldest and emptiest and most featureless possible state, quantum fluctuations continue. They cannot be stopped by thermodynamics or entropy, or the expansion of space or anything else in the physicist's toolkit. The uncertainty principle guarantees that energy and position and momentum can never be perfectly simultaneously determined, which means that even a universe in its deepest possible rest is still, at the most fundamental level, flickering, trembling, not with warmth or complexity or anything you could see or feel, but with the irreducible quantum noise that is, it seems, the universe's most indestructible property. Something, even at the end of everything, refuses to be perfectly nothing. And in that refusal, in that last trembling of quantum possibility in the cold of the Dark Era, there is the seed of something we have not talked about yet. Something that changes the meaning of everything that came before it. Something that transforms the end into a question rather than a period. And that question is what we're going to explore next. There is a question that has haunted philosophers and physicists alike for as long as human beings have been capable of asking it. It is a question that feels almost too large to ask seriously. Too presumptuous, too much like wishful thinking dressed in the language of science. And yet the mathematics of quantum mechanics raises it with complete seriousness, without sentiment, without any interest in whether the answer is comforting or terrifying. The question is this: what if it does not end? What if the Dark Era, that vast cold ocean of near-nothingness stretching across timescales beyond all comprehension, is not the final chapter, but simply the longest intermission in a story that has no last page? What if the universe, given enough time, and in the Dark Era there is nothing but time, eventually finds a way to begin again? Not because something miraculous intervenes, not because any law of physics is broken or bypassed, but because quantum mechanics, applied with absolute consistency across infinite time, makes the impossible merely very, very improbable, and improbable, given infinite time, eventually becomes inevitable. To understand how this could work, you need to know about something called a Boltzmann brain, named after the 19th century Austrian physicist Ludwig Boltzmann, who first began thinking seriously about the long-term fate of a universe governed by thermodynamics. Boltzmann understood that in a universe at maximum entropy, a universe in the condition of the Dark Era, where everything is uniformly cold and diffuse and featureless, random thermal and quantum fluctuations still occur. They have to. The laws of physics do not permit perfect stillness at the quantum level, as we explored in the last chapter. And here is the strange implication of that fact. Given a sufficiently long time, random fluctuations can by pure chance assemble themselves into ordered structures, extraordinarily unlikely ordered structures that would normally require vast amounts of energy and time and physics to build through any organized process. Given enough time, and in the Dark Era time is the one thing present in unlimited supply, quantum fluctuations could, in principle, spontaneously assemble anything, a single particle, a molecule, a rock, a planet, a star, an entire functioning brain, complete with memories of a life it never actually lived, flickering into existence for a moment before dissolving back into the void. The mathematics allows it. The timescales required are staggering almost beyond description, but they are finite. And in an infinite future, finite probabilities eventually occur. The concept of a Boltzmann brain is partly a philosophical puzzle and partly a genuine challenge to cosmological thinking, and I do not want to dwell on it too long as anything more than a signpost pointing toward the deeper question. Because the Boltzmann brain is actually a relatively small fluctuation compared to what we are really asking about. What some physicists have seriously proposed is that a sufficiently large quantum fluctuation, one incomprehensibly larger and rarer than a Boltzmann brain, but not forbidden by any law of physics, could spontaneously create a new low-entropy state from the featureless uniformity of the dark era. A new pocket of order, a new concentration of energy in a small region of space. Something that behaves, in its essential physics, the way the very early universe behaved in the first fraction of a second after the Big Bang. Something, in other words, that could be the seed of a new universe. Not continuation of the old one, not a rebirth in any mystical sense, but a genuine physics-driven spontaneous fluctuation into a new ordered state that then expands and evolves according to the same laws that governed everything we have followed on this journey tonight. The timescales involved in waiting for such a fluctuation are numbers that make even the Google years of black hole evaporation look small. We're talking about timescales expressed as 10 to the power of 10 to the power of 10. Numbers so large that the exponent itself requires an exponent, and the language of ordinary mathematics begins to groan under the weight. But here is the crucial point, the one that transforms this from idle speculation into something genuinely worth sitting with in the dark. If the universe's future is truly infinite, if space continues expanding forever, and the dark era stretches on without any final termination, then no matter how improbable a fluctuation is, no matter how many zeros you need to write the waiting time, eventually that waiting time is reached. In an infinite future, every finite probability is not just possible but guaranteed to occur, and to occur again, and to occur infinitely many times. The universe, on this view, is not heading toward a final ending. It is heading toward an endless series of new beginnings, each one separated from the last by timescales of inconceivable length, each one a brief bright flowering of order and complexity in an ocean of cold equilibrium. Now, I want to be honest with you about the status of these ideas because intellectual honesty is something I believe you deserve, especially here in the quiet of the night when you are weighing these things at their full emotional weight. The scenario I have just described, the spontaneous quantum fluctuation into a new low-entropy state, the potential for new universes emerging from the dark era, is a theoretical possibility, not an established fact. It rests on assumptions about the infinite future of the universe, about the behavior of quantum mechanics at timescales. No experiment will ever probe, and about the nature of probability in an infinite universe, all of which are subjects of genuine and unresolved debate among physicists and philosophers. Some physicists take this possibility very seriously, others find it problematic in ways that are subtle but important. We do not know if the universe's future is truly infinite. We do not know if quantum fluctuations behave in the dark era the way our current equations suggest. We do not know if there is some deeper law of physics, currently beyond our reach, that places a genuine final boundary on the universe's story. These are open questions. They are among the most open questions in all of science. But what I find most extraordinary about this possibility is not whether it is true, it is what it does to the meaning of the journey we have taken tonight. If the universe can begin again, if the dark era is an intermission and not a finale, then the death of the last star is not an ending in any final sense. It is a transition, a vast, cold, dark, almost unimaginably long transition, but a transition nonetheless. The fire goes out, the darkness descends, the cold settles in for timescales that make all of stellar history invisible, and then, somewhere in the infinite patient waiting of the quantum vacuum, something stirs. Something fluctuates in the right direction, and the universe, which never truly stopped existing, begins to become interesting again. Whether that new universe resembles ours, whether it has the same physical constants, the same laws, the same capacity for stars and planets, and life and consciousness, we cannot say. It might be entirely different. It might be entirely inhospitable to anything we would recognize as complexity. But it would be something, and something, after the long cold nothing of the Dark Era, is everything. Lie here for a moment and let that idea settle into you. The universe we inhabit, with its stars and its darkness and its 13.8 billion years of history and its 5 billion year future before our sun dies, may be one iteration in a sequence that has no beginning we can identify and no end we can locate. The last star dying may be, in the longest possible view, just one more moment in a story that keeps finding ways to continue. I cannot promise you that is true, no one can, but the mathematics does not forbid it. And in a universe this strange, this deep, this full of surprises at every scale we have ever been able to examine, the fact that the mathematics does not forbid it feels, on a quiet night like this one, like something worth holding on to. We have travelled a long way tonight. We have moved through epochs so vast that the numbers describing them stopped feeling like numbers and started feeling like the names of foreign places. Real, in theory, but impossible to truly visit. We have watched the last stars burn down one by one across 100 trillion years. We have drifted through the degenerate era among the cooling ghosts of white dwarfs and silent neutron stars. We have waited, in imagination, through the almost incomprehensible length of the black hole era, as the universe's last great structures evaporated particle by particle into the cold. We have stood at the edge of the dark era and felt, if only briefly and imperfectly, something of what it means for a universe to approach its own thermodynamic stillness. And now I want to come back, not all the way back to tonight. We will do that gently, in our own time, but back to the scale of living things, back to the question that I think underlies everything we have explored, the question that most people are really asking when they find themselves drawn to this subject in the quiet of a late night. What does all of this mean for us? For life? For everything that has ever thought or felt or wondered? What does it mean that all of this light, all of this complexity, all of this extraordinary improbable richness exists inside a window of time that, on the full scale of the universe's story, is almost vanishingly brief? The first thing I want to say is this: the window is real, and it is enormous, and we are inside it right now. The Stelliferous Era, the age of stars, lasts approximately 100 trillion years. 100 trillion years of galaxies blazing with light, of stellar nurseries producing new suns, of planets forming around those suns, of chemistry becoming complex enough in the right conditions to become biology, of biology becoming complex enough in the right conditions to become consciousness, of consciousness becoming curious enough to look up at the night sky and ask questions about what it sees. 100 trillion years is the budget. That is how long the universe funds the project of light and warmth and the possibility of life. And while that budget will eventually be exhausted, as we have seen in intimate detail tonight, it is not nothing. It is, by any honest accounting, an extraordinarily generous allocation of time. The tragedy is not that the window closes. The tragedy, if there is one, is that we so rarely notice we are inside it. We are living right now in what may be the most eventful and richly populated era the universe will ever know. Think about what that actually means. The universe will exist in some form for timescales that make the current age of stars look like a single frame in a very long film. The vast majority of the universe's future, measured in raw years, will be cold and dark and empty of anything resembling the complexity we see around us tonight. There will be no more stars, no more planets, no more oceans or atmospheres or seasons or weather, no more chemistry energetic enough to build molecules of any interesting complexity. No more biology of any kind that we can currently imagine. The universe's future is, overwhelmingly, a future of decreasing complexity, decreasing energy, decreasing structure. And we are here at the beginning of it all, in the brief, bright opening act, in the era when the universe is doing the most interesting things it will ever do. We are not late arrivals to a party that is winding down. We are early guests at a celebration that will be followed by an almost eternal silence. Every civilization that has ever existed, or that will ever exist, lives within the Stelliferous Era. This is not a guess or a philosophical position. It is a straightforward consequence of the physics we have explored tonight. Life as we understand it requires energy, and the only sustained, reliable source of energy in the universe is stellar fusion. No stars means no energy gradient steep enough to drive the chemical complexity that life depends on, which means that every species that has ever evolved on any planet around any star in any galaxy, throughout all of cosmic history, every creature that has ever breathed or grown or reproduced or experienced anything at all, has lived within this same window of 100 trillion years. The full inventory of all life that will ever exist in this universe is bounded on both sides by the Stelliferous era. Before it, the universe was too young and too energetic and too different for biology. After it, the universe will be too cold and too empty and too uniform for the chemistry life requires. The window is 100 trillion years wide and we are inside it, and nothing that lives will ever exist outside it. There is something in this that I find both humbling and unexpectedly deeply moving. Every act of love or curiosity or courage that has ever occurred, every moment of joy, every instance of kindness, every work of art or science or philosophy that any conscious being anywhere in the universe has ever produced, all of it happened here, inside this window, in the warm, bright era of the stars. All of the meaning that has ever existed in this universe, all of the experience and knowledge and beauty and grief and wonder, it is all a product of the Stelliferous era. It belongs entirely to the Age of Light, and the Age of Light, vast as it is on human timescales, is itself just a brief island of order and complexity in an ocean of cold and dark that stretches out on either side of it across a depth that thought can barely touch. We are not permanent, but we are here. And the fact that anything as improbable and extraordinary as awareness and feeling and curiosity arose inside this window and noticed the window and wondered about what lies beyond it, that is not something the universe arranged on purpose. It is something that happened against enormous odds in the time that was available. And it seems to me, lying here in the dark thinking about it, that this makes it more remarkable, not less. What about the civilizations we will never know? The ones that may have arisen on worlds around stars that burned before the Earth existed, that lived and built and wondered and then fell silent billions of years before any human mind could have reached across the distance to find them. Or the ones that may arise in the far future, around the last red dwarfs burning in the twilight of the Stelliferous era, on cold, dim worlds orbiting stars so faint they barely register as more than embers. All of those civilizations, past and future, known and unknowable, share the same cosmic address. They live inside the same window. They are warmed by the same physics, threatened by the same eventual darkness, bounded by the same fundamental constraint. In that sense, every conscious being that has ever existed or will ever exist in this universe is our contemporary in the deepest possible meaning of the word. Not contemporary in time, the separations are enormous, but contemporary in condition. We are all together, the universe's brief experiment in knowing itself, crammed into the narrow bright window between the first stars and the last. And here is what I keep returning to, in the quiet at the end of a long night of thinking about all of this. The universe did not have to produce anything that could notice it. The laws of physics did not require consciousness as an outcome. There was no guarantee, written anywhere in the equations, that matter would become complex enough to wonder about its own origins and its own fate, and yet it did. You are here, tonight, wondering. The universe spent 13.8 billion years producing something capable of looking back across all of that time and asking what it means and feeling something about the answer. That is not nothing. That is, in fact, the most extraordinary thing I can think of. Not the scale of the universe, impressive as it is, not the timescales, staggering as they are, not even the long, dark future ahead. But the fact that right now, in this particular moment of the universe's history, there is something it is like to be here, something it is like to lie in a quiet room and think about the last star dying, something it is like to feel the weight of all that darkness ahead and still, somehow, feel grateful for the light. I want to tell you something about your body that you may have heard before, but that I do not think you have ever fully felt. The atoms that make you up, the carbon in every cell of your body, the oxygen moving through your lungs right now as you breathe slowly in the dark, the iron carrying that oxygen through your blood, the calcium that gives your bones their hardness, the nitrogen woven through every strand of your DNA. None of those atoms were here at the beginning. The universe, in its first moments after the Big Bang, contained almost nothing except hydrogen and helium, the two simplest elements, forged in the first 3 minutes of existence when the cosmos was hot enough and dense enough to fuse protons together into the lightest nuclei. Everything else, every element heavier than helium, every atom of carbon or oxygen or iron or gold, or any of the dozens of other elements that make up the periodic table, had to be built. And the only forge in the universe powerful enough to build them, the only crucible hot enough and dense enough to assemble complex nuclei from simpler ones, was the core of a star. You are here because stars died. Not metaphorically, not as a poetic approximation. Literally, physically, in the most concrete and measurable sense, the atoms that compose your body were processed inside stars that no longer exist. The first stars in the universe were nothing like the stars we know today. They formed from clouds of almost pure hydrogen and helium, the primordial mixture left over from the Big Bang, without any of the heavier elements that help modern gas clouds cool and fragment into the modest-sized stars like our Sun. Because they lacked these cooling agents, the first stellar clouds collapsed into objects of extraordinary size. These first stars, which astronomers call Population 3 stars, are thought to have been enormously massive, perhaps hundreds of times the mass of our Sun, perhaps more, and they burned with an intensity that makes any modern star look restrained by comparison. They blazed with ultraviolet radiation that ionized the surrounding gas, carving enormous cavities of light in the early universe. They fused hydrogen into helium, helium into carbon, carbon into heavier and heavier elements, pushing the synthesis of new materials up through the periodic table in their cores. And then, because they were so massive, they burned through their fuel with reckless speed and died young, in titanic supernova explosions that scattered their contents across the surrounding space. Those explosions seeded the early universe with the first carbon, the first oxygen, the first of every element heavier than helium that the universe had ever contained. And in doing so, they made everything that came after possible. The atoms those first stars scattered did not immediately become you. The journey from a supernova explosion in the early universe to the body you're inhabiting right now is a long one, with many steps and many lifetimes of stars in between. The enriched gas from the first stellar explosions mixed with surrounding hydrogen clouds and eventually collapsed into second-generation stars, smaller, more varied, longer-lived, carrying within them the heavier elements seeded by the first generation. These second-generation stars fused those elements further, built new and heavier atoms in their cores, and eventually scattered them in their own deaths. And so the cycle continued. Generation after generation of stars living and dying and returning their enriched material to the interstellar medium, each cycle adding more complexity to the chemical inventory of the cosmos. By the time our Sun formed, 4.5 billion years ago, from a collapsing cloud in the Milky Way, that cloud already contained the accumulated legacy of many previous stellar generations. The carbon and oxygen and iron and everything else that eventually became the Earth, and the oceans and the first cells and every living thing since. All of it was there in that cloud because stars had been living and dying and enriching the cosmos for 9 billion years before our solar system ever formed. Think about what it means that this is true. You are not separate from the stars. You are not a visitor to a universe that was built from stellar fire. You are a product of it, in the most direct and literal sense possible. The iron in your blood was forged in the core of a star during the final stages of its life, when the fusion chain had progressed far enough to produce iron nuclei, and it was scattered into space by the star's supernova explosion billions of years before the Earth existed. That iron travelled through the interstellar medium, perhaps for hundreds of millions of years, before it was swept up in the collapse of the gas cloud that became our solar system. It settled into the forming Earth. It was incorporated into minerals, into rock, into the early oceans. It became part of the first biochemical systems that evolved the ability to use it in oxygen transport. And eventually, through billions of years of biological evolution, it ended up inside you, carrying oxygen to your brain right now as you lie here in the dark. The journey from stellar core to your bloodstream took billions of years and passed through a chain of processes so improbable that it genuinely beggars the imagination. And yet here it is. Here you are. The carbon in your body has a similarly extraordinary history. Carbon is made primarily in medium-sized stars through a process called the triple alpha process, in which 3 helium nuclei fuse together to form a single carbon nucleus. This process occurs in the later stages of a star's life, when the hydrogen in its core has been exhausted and the star begins fusing helium. The carbon produced in these stellar cores is eventually scattered into space when the star dies, expelled in the stellar winds of a red giant, or blown outward in a planetary nebula, or scattered explosively in a supernova depending on the star's mass. That carbon then drifts through space until gravity gathers it into new clouds, new stars, new systems. The carbon that makes up your body, every organic molecule in every cell, the backbone of your DNA, the structure of every protein, was built in stars and scattered by their deaths, and gathered again by gravity into the cloud that became our solar system. You are, in the most precise chemical sense, recycled stardust. Ancient, processed, extraordinary stardust. And now, bring this back to the journey we have taken tonight. We have followed the universe forward to the death of the last star, to the cooling of the final red dwarf, to the long darkness of the degenerate era, and the black hole era, and the deep dark beyond. We have watched, in imagination, as the last nuclear fire anywhere in the cosmos sputters and goes cold. And in that context, this fact about your body, that you're made of stellar material, that the atoms composing you right now were processed in stars that lived and died before the Earth existed, takes on a meaning that I find almost unbearably beautiful. You're not just watching the story of stars from outside, you are made of them. You are, in the most literal physical sense, a part of the stellar era. The stelliferous era is not something that happened out there, at a vast and impersonal distance, in a cosmos you were dropped into by accident. It is something happening inside you, right now, in every atom of every cell of your body. The ion carrying oxygen to your brain is the stelliferous era, metabolizing. The carbon in your thoughts is the stelliferous era, thinking. You're not an observer of cosmic history. You're a vessel for it, a temporary and conscious arrangement of atoms that the universe spent billions of years building through the deaths of countless stars, given briefly the extraordinary capacity to know what it is made of and to feel something about that knowledge. The last star dying does not erase this. It completes it. The circle that began with the first stellar explosion seeding the universe with complexity ends, eventually, in the long dark after the final light. But in between, right here, right now, in the warm middle of the stelliferous era, the universe's investment in complexity produced something that could look up at the stars and recognize them as kin. That recognition, quiet and real and yours right now in the dark, is perhaps the most remarkable thing the universe has ever done. We have reached the end of our journey. Not the end of the universe. That, as we have seen, is something so remote and so strange that the word end barely applies to it. But the end of tonight's voyage through deep time, through the death of stars and the cooling of remnants, and the long, patient darkness that follows everything that has ever burned. And I want to bring you back now, slowly and gently, the way you come back from a very deep place of thought, not all at once, but in layers, returning first to the scale of galaxies, then to the scale of our own, then to the solar system, then to this planet, then to this night, then to this room, then to the simple, extraordinary fact of you, lying here, breathing, alive, aware. Because that is where this journey was always heading, underneath all the numbers and the timescales and the epochs and the physics. It was always heading back here, to this moment, to you. The universe is approximately 13.8 billion years old tonight. It has been making stars for almost that entire time, and it will continue making them for roughly another 100 trillion years before the last stellar nurseries go dark and the final generation of red dwarfs burns alone in the increasing emptiness. That means we are, right now, in the first fraction of 1% of the stelliferous era. We are not at the twilight. We are not even at the afternoon. We are at the bright, early morning of the age of stars, closer to the beginning than to the middle, surrounded by a cosmos that is still relatively young and still relatively full of fire. The night sky above you, with its thousands of visible stars and the faint river of the Milky Way, if you are somewhere dark enough to see it, is not a relic or a remnant or a fading echo. It is the universe in its prime. It is the cosmos doing what it does best right now, at full capacity. And you are here for it. You are awake inside it. You are, tonight, a conscious part of the most luminous era the universe will ever know. I've been thinking, as we have travelled through all of this together, about what it means to hold the full arc of the universe in mind at once, to know, genuinely know, that the stars are temporary, and the darkness ahead is vast, and the light around us now is precious in a way that the universe itself cannot feel, but that we can. And what I keep arriving at is not grief, though grief would be understandable. What I keep arriving at is something closer to wonder, sharpened by awareness. The stars are beautiful on any night you care to look at them, even without knowing any of this. They have always been beautiful to every human eye that has ever turned upward in the dark since the first of our kind looked up and wondered what those lights were. But when you know what a star actually is, a temporary fire burning against entropy, fusing the atoms that will one day become other things, including perhaps living things, including perhaps conscious things, the beauty changes character. It deepens, it becomes specific. It carries the weight of what it actually is, rather than just what it looks like. And that, I think, is what science gives to wonder. Not a replacement for it, a deepening of it, a way of looking at the universe that makes it more astonishing, not less. You are the universe noticing itself. I know that phrase has been said before, by thinkers wiser and more careful than me, and I know it can sound like a comfortable abstraction, something you nod at without quite feeling. But tonight, after everything we have explored together, I want you to feel it, rather than just hear it. The hydrogen in your body is almost as old as the universe, formed in the first 3 minutes after the Big Bang, drifting through space for billions of years, eventually gathered by gravity into the cloud that became our solar system, becoming water, becoming life, becoming you. The heavier elements in your body were forged in stellar cores and scattered by stellar deaths across billions of years of cosmic history. Your consciousness, the thing that is processing these words right now, that feels something about what they mean, that can reach across 13.8 billion years of time with its imagination and stand at the edge of the last light and feel the weight of it. That consciousness is what the universe has produced in this small corner of itself after 4.5 billion years of planetary chemistry and biological evolution. You're not a small thing looking at a large universe from the outside. You are the universe, here, looking at itself from the inside. And the looking, the wondering, the feeling of scale and awe and the quiet vertigo of comprehension, all of that is the universe doing something it has almost never done, and may, in the long cold future we have travelled through tonight, never do again in quite this way. The next time you go outside on a clear night and look up, tomorrow, or next week, or on some cold, clear winter evening when the stars are sharp and near seeming in the dark, I want you to carry something with you from tonight, not dread, and not sadness, and not the paralysing weight of cosmic scale. Carry instead this: every star you can see is burning right now. Actually burning, actually fusing hydrogen into helium in its core at this precise moment, actually maintaining that extraordinary balance between gravity and fusion that produces light and warmth and the possibility of everything complex. Every point of light in that sky is a fire that has been burning for millions or billions of years, that will keep burning for millions or billions more, and that will eventually on its own timescale run its course and go dark. But tonight it is burning. Tonight, the light is real and present and crossing the distance between that star and your eye at 300,000 kilometers per second, arriving at you after a journey of years or centuries or millennia, entering you through the most sensitive optical instruments in the known universe, your eyes, and producing in you an experience of beauty and scale and connection that no other arrangement of matter in the cosmos that we know of is capable of having. That is not ordinary. That has never been ordinary. It is, by any honest accounting, one of the most extraordinary things in the universe. Thank you for staying with me through all of this tonight. Thank you for giving your time and your attention and your imagination to a journey that goes to some of the strangest and most remote places that human thought can reach. If this exploration has moved something in you, if it has shifted the way you will look at the night sky or think about the light that reaches you from distant stars, then something real has passed between us in the dark of this shared night, and that means something to me. We are the universe noticing itself, and tonight we notice together. If you enjoyed the journey, a like on this video or a subscription to the channel is a small thing that makes an enormous difference. It helps more curious minds find their way to these quiet late-night voyages through the cosmos, and that is a worthwhile thing to help happen. We are the universe that decided the stars were worth thinking about. Keep thinking about them. Keep looking up. And when you do, remember what you now know, that the light reaching your eyes is ancient and temporary and precious, that the darkness ahead is vast but not yet here, and that you are alive in the brightest moment the universe may ever know. Sleep well tonight, somewhere warm and safe inside the stelliferous era, with 100 trillion years of starlight still ahead. The stars are burning, they are burning right now, and they are burning for you. Good night.